Hey everybody, so here is finishing up the problem for the distributed loads. So last time we finished up on the link problem, so we're looking at these tree chops and how this weight is distributed. And so we left off with having drawn the model for the distributed load, and what we need to do is now find out what the resultant force is right here, and also figure out where the location is of that resultant force. So let's go ahead and do that. So the first thing that we need to do after we've done this model is we need to determine what our resultant force is for each force. Let me make this a little bit bigger. So for the first force, which we will call FR2 that we want to find is just equal to, since this is a triangle, it's the area of that triangle, so that's just one. I keep switching my eraser here. 1/2 base times the height. So the base of this triangle here would be 30 feet. So I have 1/2 30 feet. And the height of that is going to be W, because that's the maximum weight from this distributed load, or the maximum intensity of this distributed load. So that one here was just 1 kip per foot. And this then will result in 15. And then the unit here is kips. Okay. And this, of course, if it's a vector, would be in the J direction, and it would be down. So it would be negative. The next one we do is the one for the right side. So that's R1, resultant force for the right triangle. So again, it's the same equation, the area of that triangle, 1/2 base times height. And for this one here, our base, instead of it being 30, it's 20. So we got 20 feet, multiplied it by 1 kip per foot, because the intensity is the same since they all meet, both these triangles meet at the same point here. And that will give us 10 kips. And if this is a vector, it's also negative and in the J direction. Okay, so that's cool. Now we want to find the total resultant force. So FR is equal to the sum of the resultant forces from each shape. So I'll just put I. So that one here is going to be our negative 15 plus our negative 10. And this is all in kips and in the J direction. So that will equal negative 25 kips in the J direction. So this is the total resultant force due to both of these distributed loads. So this blue guy right here. Okay. Again, negative because it is going down. So the next part is then to find the location of this resultant force. So here we can use our moment equation. So we have moment about some point O is equal to the moment arm, the perpendicular distance, to the resultant force. So here, this is also equal to the sum of the moments of each force individually, about point O, plus whatever couple moments that we have, which we don't have any couple moments in this problem, so this just goes to 0. So if we want to figure this out, we have not calculated what this value is, which is fine, but we can calculate this one. So we have D, perpendicular moment arm, of the resultant force, and that would be equal to, we have the moment arm for the first resultant force plus the moment arm for the second resultant force. So before we go any further, we need to go and check what directions these moments are going to be. So we defined point O to be over here on the left. So if each of these forces are generating moment about O, then we could see, since they're all pointing down, that they will all be going in the clockwise direction. So each of these moments are going to be negative. So that's good. We'll go down here and we'll change all of these signs to negative, 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 negative. So I'm going to put just a note here. Each moment is negative about O, because it's clockwise. Okay, so now we can put in our known values. So we don't know D perpendicular, that's what we're trying to find, but we do know the resultant force, which was 25 kips. And remember that this is just the magnitude here, the absolute value. And then we have is equal to, so we need to find out what these D's are for each of these. So this D right here, D1, or D2, is going to be 2/3 away because the resultant force is on the heavier side of this triangle. So 2/3 of 30, it would be 20 feet. And then for this one here, we need to go all the way from O to our force. And this one here, D1, would then be equal to 1/3 of this length plus 30. So we got 30 feet plus 1/3 of 20. And this value here is equal to, I just simplified it to 30 plus 20 over 3. So let's put it down over here in our equations. So now we have negative D1, which was the 30 plus 20 over 3. This is feet. And then kips, this one here was 10 minus, we have our 15 kips multiplied by 20, which was the moment arm for that one. And we just solve for this D perpendicular. We see that all of these negatives will cancel out, and we end up getting that D perpendicular is equal to, oh, I didn't actually calculate it, but it is equal to, we got 30 plus 20 divided by 3 multiplied by 10. Let me go like this, plus 15 times it by 20, and then divide all of that by 25 here. And I will calculate that and write down the answer. Okay, so our final answer here ended up being 26.67 feet. So the next thing to do here would then be to see, does this make sense? So let's go back up to our model here, and this value is going to be 26.67, so that's about here-ish. So does this value here make sense for where our resultant force will be? And I would say yes, even though we want it to be in the center of these two, because it's more on this side of the center of these two triangles, that this triangle on the left has more force magnitude than the one on the right. So it has more influence on where it will be located. And we can see too here that it's negative 15 pounds or kips and negative 10 kips on the other side. So, but yeah, that's how you would